Good morning, everyone. My project is on the dosimetric comparison of proton therapy and cyberknife in stereotactic ablative radiotherapy treatment for liver cancer. All that means is that the bulk of my project will consist of generating treatment plans and comparing them for proton therapy and cyberknife SBRT for liver cancer. So, what is SBRT and why do we need it for the liver? The liver cancer is the third most common cause of cancer-related deaths worldwide, and the second most common site for the metastatic spread of cancer. And the liver has the unique property of being a parallel organ. This means that damage to a sufficiently small portion does not impair the function of the entire organ. For this reason, surgical resection is the gold standard for treatment. However, only about 30% of patients are eligible. This brings about the need for an alternative form of treatment, and this is where SBRT comes in. So in radiotherapy, there are two main goals. The first is to deliver the maximum dose to the tumor, and secondly, to the minimum dose to the surrounding normal tissue. SBRT is able to achieve this by the precise delivery of very conformal and high radiation dose to the tumor and minimal dose to the surrounding tissues over a few fractions. But the successful implementation of SBRT requires adequate patient immobilization, a technique to manage respiratory motion, and image guidance to allow precise delivery to the planned target volume, which is the volume of tissue that is selected to ensure that the tumor receives the prescribed dose. It consists of a gross tumor volume, which is the gross demonstrable extent of the tumor, the clinical target volume, which is the GTV, plus the suspected microscopic extension of the disease, the internal target volume, which accounts for all the possible locations that the tumor might occupy due to organ motion on account of respiration and the deformable nature of the liver, and a setup margin to account for geometrical uncertainties in patient positioning and the treatment machine. The goal of patient immobilization, respiratory management, is to basically reduce the ITV by as much as possible or to remove it completely. So there's about 4 respiratory management techniques used for liver SBRT specifically. They include abdominal compression, active breathing control, where the breathing of the patient is frozen to allow the radiation beam to concentrate on the tumor, and respiratory gating, where the patient's breathing is tracked real time and radiation is delivered only during specific phases of the patient's breathing cycle, and real-time tumor tracking. The first 3 represents techniques that can be used by proton therapy, while cyberknife uses real-time tumor tracking. Ultimately, the goal is to reduce the planning target volume as much as possible to spare normal tissues. So what is cyberknife? Cyberknife combines a small 6 megavolt linear accelerator with an image-guided robotic system to deliver a photon-based SBRT. It has 6 degrees of freedom and a repositionable treatment couch that allows for a wide array of non-coplanar beam angles, which allows for highly conformal dose distributions to be achieved. It also has image guidance using 2 orthogonally placed digital X-ray images and a computerized targeting system. The combination of the image guidance and the computer-controlled robotics allows for continuous tracking, detecting, and correction for tumor and patient movement throughout the treatment. Essentially, it allows the ITV to be removed or reduced. And then we get to proton therapy, which has emerged as a very suitable modality for the implementation of SBRT. This is due to the favorable depth dose profile of protons that allows for dose escalation while keeping a certain volume of tissue free from receiving any radiation. This is due to the physics of proton particles, which is that proton is a positively charged particle That is about 2,000 times heavier than an electron. This means that the rate of energy loss in matter is proportional. For charged particles, the range of energy loss in matter is proportional to their mass and inversely proportional to the square of their velocity. This means that as the proton traverses in matter and its speed decreases, more and more energy is being deposited in tissue, such that towards the end of the range of the particle, there is a sharp increase in the dose deposited, resulting in a bright peak, followed by a rapid fall off to zero after. This means we can design treatment plans using proton therapy that have virtually no exit dose and no dose behind the tumor. In contrast to photon beam, which has an high entrance dose and a non-zero exit dose, this means that photon beams result in radiation to tissue proximal and distal to the tumor. The other thing to note is that for proton therapy, in order to achieve the uniform and conformal dose distribution, multiple beams with varying energy are needed to create what is called a spread out bright peak. The other thing to note is that protons are more biologically damaging than photons. This is due to the spacing of ionization events of protons relative to that of photons. Protons are more densely charged. The protons cause more closely spaced ionization events, resulting in more irreparable damage to the DNA, resulting in more cell killing. Right now, the current accepted practice is to assume that protons are 10% more damaging than photons. This is being challenged because it's been shown that the relative effectiveness of protons to photons changes with the rate of energy with depth into the tissue as the rate of energy loss changes. In terms of the delivery method for proton, only pulsar beam delivery will be considered, in which the proton beam exits the particle accelerator as a collimated spot. The beam is then manipulated by a means of electromagnets which cause a magnetic deflection that controls the lateral direction of the beam. The penetration depth of the proton is controlled by the energy, and the local dose deposition is controlled by the number of protons, which just means the beam on time. By controlling these three parameters, the highest level of conformity can be achieved using proton therapy. Basically, we can stack the dose in the tumor volume in a similar fashion to stacking an empty jar with marbles. So what are the aims of the project? The application of CyberKnife SBRT and proton beam therapy for the treatment of liver cancer is relatively new, and there is no data, as far as I know, comparing the two modalities. So the primary aim of the project is to create a protocol for the treatment planning comparison of CyberKnife SBRT and proton beam therapy for the treatment of hepatocellular carcinoma and liver metastasis, which are primary and secondary forms of liver cancers. This will hopefully allow for a determination of which treatment modality is superior on a case-by-case level, and an identification of factors that might favor one modality over the other. And as a secondary objective is to implement a level of automation that will allow for a relatively efficient comparative analysis to be performed on a case-by-case level using outputs from just the treatment planning software. So why is this project needed? The go-ahead has just been recently given to begin construction on Australia's first proton facility in South Australia. But in order to achieve an highly efficient outcome using proton therapy, it is important to accurately identify the patient groups that are most likely to benefit. The new proton facility can only treat so many patients in a given year. So it's important to make sure that patients for which proton therapy offers a superior outcome when compared to available photon-based treatment modalities are chosen or referred. So how do we quantify superiority? What analysis steps are needed? What metrics should be used? Or what thresholds or scoring system should the clinicians use? The protocol will hopefully answer these questions and more. And the plan to do this starts by generating some retrospective treatment plans, evaluating the treatment plans, comparing the plans, and performing an analysis of the results, investigating the possibility of automation, and generating the final protocol at the end. So stage 1, the research plan. With collaboration from St. Charles Gardner Hospital and Royal Adelaide Hospital, 10 patients who have been previously treated for HCC and liver metastasis will be selected. Royal Adelaide Hospital will provide patient data, two of which they'll provide patient data as well as 2 proton plans. One using PTV1, which does not include the ITV, to simulate image guidance and negating treatment, and PTV2, which simulates which represents a treatment where there is no image guidance or gating. And St. Charles Gardner will produce a CyberKnife SBRT plan using PTV1. So the planning constraints that the treatment planners will use will include a dose to the tumor of 54 grays in 3 fractions for liver metastasis and 45 grays in 3 fractions for HCC. The dose to normal tissue will be based on the UK consensus on normal tissue dose constraints for stereotactic radiotherapy. The constraints will be entered into the planning software as objective functions, and a mathematical measure of the violation of each objective is defined by the software. For each objective, a weighting factor is introduced to adjust the relative importance of the objective functions according to the clinician's preference. A trial and error process is then initiated till a plan that best satisfies the objective functions is generated. For proton therapy, there's an extra step called robust optimization, where a weighting is assigned to each beam direction that gives an indication of its sensitivity to setup errors, internal motion, and range uncertainties. At stage 2, we have the treatment plans evaluation. At this stage, we will examine how well the generated plan satisfies the planning constraints, identify critical areas of the plan that could lead to significant improvements in the generated plan. The reason why is we don't want to be comparing a rubbish plan with a good plan. We want to make sure that the plans are of a decent standard to allow for a good analysis later on. This will be done by using suitable metrics related to tumor control probability and normal tissue complication probability. After this, a robust evaluation is performed where errors due to setup, internal motion, and the range are simulated using a worst case scenario. The plan is to compare the simulated dose distribution with the planned dose distribution to see what the difference is, and which will give an indication of the robustness of the treatment plan. After this, the treatment plans will be compared. At this stage, the plan is to develop a system that scores the treatment plans in a manner consistent with clinical practice, using criteria such as the dose volume data, robustness, stability, treatment time, planning time, and hopefully identify clinically relevant differences between the plans. And then we get to stage 4, where we analyze the results and look for trends in the results that indicate factors that might favor one treatment modality over another. And at stage 5, investigate the possibility of automating the entire analysis step. And then stage 6, where we generate the protocol. The goal, or when everything is said and done, the hope is that the outcomes of the project can become part of a clinical decision support system that will allow clinicians to be able to efficiently compare treatment plans for CyberKnife and Proton, that will allow them to be able to select the right treatment modality for their patients, which will hopefully improve the outcomes by making sure the patients are receiving the right treatment modality specific to their disease. So that's the end of my presentation. Any questions?
My question is actually have you actually one of the questions is actually the prescription. How you define the prescription in a proton therapy and a photon. The prescription it will be the critical things because already biologically they are totally different modalities.
Yes.
How you define that? Which like you said that 54 gray and something fractions, like 3 fractions something.
Yes.
But so 54 gray in proton will be different than the photons.
Yeah, so I said right now the assumption is made that protons are 10% more damaging than photons.
Yeah.
So I didn't talk about the RBE because I didn't have time. So the relative biological effectiveness right now for protons is assumed to be 1.1 for every situation.
Okay.
So in a real situation, in keeping with that standard, the dose prescription for photons will be divided by that number to get the dose for a photon treatment. Mm-hmm. But the fact is that the RBE it's not fixed. It changes as a function of the energy deposition rate, which is also called the linear energy transfer. Yeah. So, which actually changes with depth into the tissue. Some studies have shown that at the Bragg peak, the LET is different from this point here. So the 10% is like an average, but in reality, we are treating with the highest point. So there's a lot of challenge as to why we're using 1.1 or decrease. And part of the project will be to do some biological modeling to see what effect that would have on the treatment, on the outcomes.
So that one of the tool you will use to evaluate the plan is the biological model?
Well, it's something I'm doing as an aside.
Okay.
It's not something
it's
not something that Royal Adelaide Hospitals because they are the ones that will be using.
So what prescription they will use for the program?
It will be this prescription divided by 1.1.
1.1, okay.
Yeah, that would be what they would use. Where is it? Yeah.
It sort of feeds off what Tala's question was as well, in terms of you're going to compare two plans using two different calculation methods or algorithms, and are they going to be that comparable? Because in theory, CyberNet is either going to use a ray tracing or Monte Carlo types of calculation, and a proton is going to be a different type of calculation. So in terms of planning accuracy, is it able to be that easy to compare them?
Well,
that's a bit of a loaded question, but
like one of the steps for me is to increase my knowledge on the subject. The truth is, I don't know what algorithm they're using in Adelaide.
Okay.
But all I know is that they will be doing a robust optimization and robust evaluation where they will assume the worst case scenario for their treatment plans and see how that changes. With Proton, there is a lot of things that like, for example, there's a lot of things to consider with protons. Where is it? I didn't have space, so I didn't want to put anything extra in. For example, the range in matter is dependent by the stopping power and the energy. So the stopping power is generated using CT data, which is based on electron density. But it's possible for two different tissues to have the same electron density and different stopping power, which means the range is not actually accurate. So when we specify the margins, so if you can see here, in photons we specify margins based on what's it called? Based on like what's the word? Okay, in photons you can see the energy, the beam just goes through. So we really, why do we have a margin here? We have a margin here because we're using multiple angles. So we need a margin to account for the different angles. In protons, if you can see, the beam stops, it doesn't continue through. So the margin is specified for this part of the beam using the range uncertainty, not the geometric uncertainty. And so there's so much that is honestly not really known, and a lot of the work for proton is based on empirical data. So just using empirical data, that's the modeling that is used in proton therapy, as opposed to photons, which uses Monte Carlo to simulate things. So you're right, there's a big difference, and that is something I can look into to see how we can reconcile those differences. Yep.
If they're all done, I have a question.
Okay.
How would you measure the dose with proton beam?
That's a big question. Well, there's a lot of research being done on that, because yeah, it's not straightforward. I don't know.
Because I don't know.
Yeah, something I need to research.
Do you have access to the tube planning here?
Not for the proton, but what thing I've seen is the whole concept of microdosimetry, which I don't know how they would use it, but I've come across it in my readings. But there's only so much room up here for the information, so I don't with stuff I don't need to right now. Still have time to gain that knowledge.
Do you have further questions?
You mentioned in your talk about that this type of the research has not been conducted.
Yeah.
So it's just mentioned in your abstract and then in this one as well. This is locally in Australia because we don't have proton before, so it makes sense to me. But have you tried to investigate internationally somewhere like the big center? What's the big center doing? How they're evaluating the patient for proton and carbonite or external beam radiotherapy? As any big center, like lots of big centers like Andy Anderson, Peter, Prince Margaret. Is anything has been already published?
I haven't found anything published. It's possible there's a lot of work. The thing is that
maybe not published, maybe some protocol has been generated.
I could try to look for a protocol, but I haven't found anything published.
Ask some MD Anderson people. There are so many people in protocol, and maybe Press Margaret as well.
It would be good to have a look for your literature review.
Yeah.
If you haven't already had those things to the literature review.
It is good to know because it can help you a lot
Yeah.
to understand the problem, and then you have also find the good tools to evaluate the plan.
Yeah.
What are the best parameters to evaluate the plan?
Yeah. That's one of the things
Yeah.
we're researching, how to actually score the different plans.
Yes. The only issue which I already talked about is the radiobiologically totally different situation. So it's very hard to. You have to have something either you can use EUD method, which is equivalent uniform dose distribution for OARs, and I don't know. It will be a challenge. Yeah, but it's a very interesting. It's very very interesting talk. Thank you.
Thanks, that was great. So you have lots of things to do. And God bless you.